Okay, we're going to finish up the discussion on surface area of composite solids. Um, saved at least this next fourth example for today because it does have a good deal of complexity to it. And there were some things that I want to show you that your calculator can help you with as well. So let's get to the fourth example. This one was it. And as it turned out, this one also proved to be, out of the 5 different shapes that we have, this one proved to be the hardest one as far as volume went as well. Now, it doesn't have anything to do with it being a triangular prism or a hemisphere or anything like that, so don't automatically think anytime you see a hemisphere that means it's going to be a difficult problem, or anytime you see a triangular prism that makes it a difficult problem, because it really doesn't have anything to do with that. It has everything to do with where various information is provided or where the information is not provided. It's simply a case-by-case basis. Okay, so you're not going to know if a problem's hard just by looking at it or not. You're going to have to get into it and see what the numbers do. All right, from our discussions of volume when we saw this shape previously, we know that this is a triangular prism plus a hemisphere. Okay, but as we discussed yesterday, surface area can be a little bit more tricky in the sense that maybe not all of the surface area is available for particular shapes, and that makes us make some adjustments. So let's start off. We do still have a triangular prism. Okay, the question is, obviously, do we have the entire triangular prism or not? Okay, what do y'all think? Okay. Yeah, okay. The entire triangular prism is there. All 5 of these the faces are represented at least in some part, but one of our faces is not complete. Okay, so how can we describe this? What are we missing? Yeah, we're missing a circle. Let's just keep it simple for this point. We have a prism that's missing a circle, right? Okay, prism missing a circle. It's probably the easiest thing that we can come up with at this point. And we have something that is added onto our our prism. Okay, so we're going to add in something extra, and that something extra is a hemisphere. Okay, and we ask ourselves the same question we ask on any shape: do we have the entire hemisphere, or does something need to be added or removed or whatever? Okay, well, let's think about this. Okay, do we have the entire hemisphere? And this is kind of a difficult question to answer. You really have to think about it, right? Um, we're thinking surface area right now. Okay, we're thinking surface area. So if we consider the entire sphere rather than just a hemisphere, okay, the skin of an entire ball, and we cut it straight through across its great circle. Okay, um, is that what we have here? Okay, yeah. So if we consider half of the surface area of a sphere, does that get us the hemisphere that we have here, or do we somehow need the circular cross section where the great circle is? Okay, well, is that great circle? Okay, is when we cut that ball in half, is that cross section, is it showing? Is it part of the surface area on this, or is it just the skin of the sphere that's showing? It's just the skin. Okay, so all we really need is the surface area of half of a sphere. So there's nothing really that needs to be done to that part of the formula. That is okay. Okay. Now let's see what information is actually required in order to get all of this done. Okay, prism. Okay, prism. How do we find the surface area of a prism? Well, you got 2 formulas on there. Yeah, you got 2 formulas on there. Okay, one of them for total, one of them for lateral. We need to make the decision whether we want total or lateral surface area. Okay, and total. Okay, we do have bases that are showing on our prism. So what was that formula again for total surface area? Okay, formula straight off the chart, pH plus 2b. Okay. Now, do we want both of the bases? Okay. I think we do. I think we do want both of the bases. Now, one of them is not complete, which is why we have the minus circle, but there's no reason for us to adjust this formula. We saw some yesterday where instead of going pH plus big B, or plus 2B, pardon me, we only went pH plus 1B because one of the bases was completely covered up and we did not need that base. But in this case, we do need both of the bases. Now, from that, we said we are going to subtract a circle. How do you find the area of a circle? Pi r squared. Hopefully we're getting that formula to the point where we don't even have to think about it. It should be pretty automatic by now. And then to that, we're going to add the surface area of a hemisphere. Okay, when you look at your formula chart, you don't have a formula for a hemisphere. We do have an entire sphere, which is 4 pi r squared. Okay, but since we only want the hemisphere, okay, yeah, then we're going to take half of that, or divide by 2, as some people are saying. Okay, so there's the formula. Now again, it's not this particular shape that makes this particular shape difficult. It's what information is provided and what information is not provided. As we're getting ready to see, there are some pieces missing in here. Okay, well, let's just see what exactly is missing. Okay, all right, P. Okay, that's the perimeter of the base, and of course we're in the red part here, so the perimeter of the base of the prism. Okay, how do we find the perimeter of the base of that prism? Okay, yeah, I think so we're saying 8 times 3, 8 units for each side times 3 sides. Okay, and that's true if all of our sides are going to be the same. Are they? How do you know this? Yeah, the problem says it's a regular base, so yes, absolutely it is. We're going to have 8 times 3 congruent sides. Okay, h in the formula refers to the height of the prism, which is how much? 11. And that needs to be added to twice the area of the base. Okay, well, our base is a triangle. Okay, and a triangle is found, area is found by 1/2 times base times height. Okay, so we really kind of need to check the base and see if what measurements we do have and what we don't have and what we need to have. Okay, so I'm going to pull the triangle off of the base of the prism and have a look at it. We know for a fact that we have 8s all around. Okay, that makes it easy as far as this is concerned. We've got the 1/2, we've got an 8 on the base. What we do not have is the height. Okay, but I think everybody can probably see, or at least should be able to see by now, that this is Pythagorean theorem. You've got 4s right there. Okay, and then we just go, okay, I've got 4 squared plus height squared, and that will equal the hypotenuse squared. 16 plus height squared equals 64. Subtract 16 to the other side, and we have height squared equals 48. And then if we take the square root of both sides, okay, then we end up with height being square root of 48. Okay, so that is our height value. We can take that to our formula and just plug it in there for now. All right, now all of that was just for the prism. Okay, now from that prism we have to subtract what? Pi. Okay, radius. Okay, what do you know about radius? Nothing. Okay, it's not there. All right, we do have some information about the circular part of this problem. Okay, this time they gave us information about the volume of the hemisphere. Okay, so again, we're going to kind of create a little space here. We can go, okay, I've got my hemisphere going on. I would love to know radius. They gave volume as 100. Okay. Now, I actually thought about not taking you down this road on this particular problem again, but I noticed something on one of the assignments that we already did and I graded and passed back. We did a particularly poor job figuring out radius based upon volume being provided. Okay. Well, let's see if we can figure this out. What's the formula for volume of a sphere? 4/3 pi r cubed. Of course, this is the entire sphere. We don't want the entire sphere. This time we want the hemisphere. So we'll take half of it. And the problem established that that was equal to 100. Okay. Now, very clear to see where the radius is. We just don't seem to have a real good idea of how to get it out of there. Now, I'll be perfectly honest. Okay, this information here should not be all that difficult. Okay, we ought to be able to at least isolate r cubed without any problem. Okay, well, let's isolate r cubed. Okay, what's going to happen to it? I got a 2 in the denominator that I do not want. Okay, so the way to get a 2 out of a denominator is to put an extra 2 into the numerator. As long as you do what to one side, you do to the other side, that's fine. That the 2's will cancel each other out. Okay. Also have a 3 in the denominator that I do not want. So I'm going to hit each side with a times 3. That'll cancel the 3's out, which is fine. Now we have a 4 in the numerator that we do not want. To get it out of there, we divide by 4. Okay, that'll take care of the 4 there. And we also have pi in the numerator. So if I divide by pi, that'll take care of that. Now, aside from kind of a whole bunch of things happening at once here, which you don't have to do them all at once, you can certainly do it in several different steps. Okay, that should isolate r cubed. Okay, the only thing that'll be left on the right is r cubed. Over here on the left, I've got 3 times 2, which is 6, times 100 is 600, divided by 4, okay, is 150, and there's a pi in the denominator. Okay, now I think here's where a lot of people got really hung up. Okay, we got r cubed. We do not want r cubed, we want r to the first. Okay, well, I kind of assumed that we would know what to do with this, and maybe I shouldn't have assumed that. Okay, if it were r squared, what would you do to get rid of the squared? Take the square root, because square and square root are opposites of each other. Okay, now it's cubed. Okay, well, are we aware that there are different kinds of roots, that square root isn't the only root that's out there? Hey, there's also a cube root, and a fourth root, and a fifth root, and a sixth root. There are as many different radicals as there are exponents. Okay, and here's the thing, guys. See, I can't separate those. What we have been doing, okay, when we had something squared, is we brought a radical into the problem. Okay, and we've called it a square root. Okay, this little symbol is not a square root. This little symbol is a radical. The operation that it performs is what we refer to as a square root. Kind of like a plus sign does addition. A minus sign does subtraction. A radical does a root of some kind. Now, what I haven't really taken any time to talk to you about is the fact that there's supposed to be a number right there called an index. Okay, and there's not a number there. But just like any other thing that you come across in mathematics, if something is not written down, then there is an automatic something that it's going to be. Okay, and if there's nothing written down here, it's automatically a 2. Okay, the index is automatically a 2. That is how come we've come to think of this thing as a square root. Okay, because that's what the second power is, square. Okay, however, if it's not a 2 on the exponent that you want to get rid of, okay, then what we're going to do is we are going to change the index to match whatever it is we're trying to get rid of as far as the exponent is concerned, which in this case is a 3. which is what we call a cube root. And if we needed to, we could make it a 4th root or a 5th root or a 152nd root. We can do it as many times or to change that index any way we want. Okay. The cube and the cube root will cancel. Okay. Cube and the cube root will cancel. Then it'll be that simple. Okay. That leaves R. The question is, how do you work this thing over here on the left? Okay. Well, for geometry students, you don't. Your calculator will. And the way you do it, it's in the math menu. And there's even an option programmed for you already. Option number 4 is a cube root. Now, I mentioned a moment ago that there are bigger roots. There's 4th roots and 5th roots and so on. You would use option number 5. And where it has that little X as the index, you would simply tell the calculator what your index is. But in this case, we're using a cube root. So hit that, and it's going to give you a cube root. Cube root of what? 150 over pi. Okay, just typing it in, and we get a value. Okay, this is our radius, 3.63 or something in the ballpark. Okay. Now, a couple of reasons I picked this. First off, I wanted to show you how to do a cube root. Secondly, I wanted to mention, you know, we've spent a little bit of time here lately talking about you do not want to round off in the middle of a problem. Okay, we don't want to round off in the middle of the problem. We only really want to round off at the end of the problem. If we round off in the middle, that's going to cause our answers to get further and further away from the right answer. Okay, so a very important question is, okay, I've got this radius here, and this value of this radius is going to have to be plugged in at least one spot in our problem that we've got going on up here. We haven't even figured it out. Okay, we've still got to figure this problem out. Okay. All right. So how do we get all of these decimal points? How do we keep all these decimal points without having to write it all down and type it all in every single time you need it? Well, the problem is the answer button is absolutely right. It will recall this number as many times as we need it for. But what happens when we type in a new line and get a new answer? Now we've lost that one. Okay, when you press answer, all it'll do is bring up the last answer that your calculator came up with. Well, whether you realize it or not, your calculator is capable of storing any data that you want to store it on. Okay, and I want to show you how to do that. Okay, right there, second button above the bottom left, above the on button says STO and then has a little arrow. That is the store function. Okay, when you press store, okay, like in my case, it said, okay, the answer is going to become, and we need to tell, we're going to give the calculator a value to store this answer as. And that's where all the little letters come in on your calculator. Okay, they're variables. We are going to assign a variable this value. Okay, and typically what I do is I just pick on the first letter in the alphabet. I pick on A, so I go alpha A. Okay, and when you press enter, the calculator will not do anything. All it has done is taken 3.627831679 and all the decimal points that are off the screen, and it has saved them all as the variable A. Now, when I'm working this problem, anytime I want this value back, all I have to do is type A. And it'll bring everything back, including all the decimal points. Okay, so I just stored my radius as A. So look what I'm going to do here in the problem. Okay, radius, where am I? There I am. Okay, pi times the radius squared, A squared. Okay, when it comes time to type all that junk in the calculator, I'm just going to bring in A there. I won't have to worry about the number or the decimal points or anything like that because the calculator's got them saved. Okay. Now, still continuing on with this mess, plus what? 1/2 times 4 times pi times the radius squared. Well, where do I have the value of radius? I've got it stored as A. That's right. Squared. And your calculator will save that value forever, either until somebody else saves a new value for A or the calculator's memory is reset. It'll save it forever. Okay, so if you ever come across a problem where you get this like this one value and you have to use it over and over and over again for 7 or 8 questions, you save that value and you've got it in there for as many times as you need it. Okay, all right, now this is looking very ugly. Okay, let's see if we can't make a little sense out of it. See if we can get a little space here. Okay, I've got 8 times 3, which is 24 times 11. Okay, simply enough, that's 264. Plus what? 2 times 1/2 times 8 times the square root of 48. Okay, well, we're going to end up with another big pile of decimal points here. 55.43. But I don't want to round off in the middle of the problem if I can help it. I'm going to need this number here in a minute to add it in with everything else that's going to be on this line. So what I'm going to do is I'm going to go store B. I'm going to pick on a new variable. And there the calculator did nothing. All it did was store the value B. What's the next term we have? Pi A squared. Okay. Pi times A squared. Okay, just like you've got it. Another big pile of decimal points. Plus 41.35. I really don't want to lose those decimal points. I'm going to go store C. There it's saved. And then lastly, we've got this term, whatever this is, 1/2 times 4 times pi times A squared. Oh, I missed pi, didn't I? Got an H in there. I hit the alpha key instead of the second key. 1/2 times 4 times pi times A squared. And that is 82.69. Okay. Well, again, I've got a big pile of decimal points. I could save this if I want, but since I'm at the end of this calculation, now I'm in a situation I can just use the answer. This 82.6940, blah, blah, blah. I can just go, you know what? That needs to be added to 264, which needs to be added to B, which needs to be added to C. And that is a whole lot easier than having to store and write down and retype all those extra decimal points. Allow the calculator to keep track of them for you. Did I miss a sign somewhere? This. Josue's absolutely right. Right there. That was supposed to be a minus sign. I lost it moving through the problem. Okay, but let's see what we have. 82.69, 402. I'll get some of the decimal points. Plus B, minus C, and plus 264. All right, so 360. Okay, what are the units of measure? Centimeters squared. Okay. Now, in 100 years, I wouldn't expect them to do anything that complicated to you. Okay, the shape is not the problem. It was the information that was or was not provided that was the problem. Okay, so a lot of steps, a lot of information you have to keep track of. Okay, we had to stop and solve a triangle problem. We had to stop and solve a hemisphere volume problem. And then we had a whole bunch of nasty decimal points working. Okay, but each and every one of the steps, there was a lot of steps, no question about it, but each step was not that difficult. Okay, I'd say probably the most difficult thing might have been this guy down here, the cube root. And that may have only been difficult because we didn't know how to do it. But now do we know how to do it? So the next time around, is it going to be difficult? No. Okay, we're back to a spot where, yeah, there's a lot of steps, but not any one of them is really all that complicated. All right, so let's take a look at the fifth and final example. This one's going to prove to be much easier, but again, it doesn't have anything to do with the shape. It has only to do with the information that is provided compared to the information that we need. Okay. Well, back when we first introduced this shape, we defined it. We decided it was a cube missing a pyramid, which is fine for starters. Okay. Surface area equals cube. Okay. The question is the same as the question always is. Do we need the entire cube? Do we have the entire cube? I mean, thinking about surface area, we have everything that the surface area would call for as far as a cube? No, we don't. Okay, what are we missing? Missing a base? Okay. Now, a cube's kind of a unique shape because it doesn't necessarily have bases and lateral faces. The reason it doesn't have those is because everything's all the same anyway. Okay, so we really need to worry about it being a base? Not really. We have a cube that is missing one of its sides. Okay, whether you want to call it a base or a lateral face or just simply call it a side, a cube can't tell the difference between its bases and its lateral faces. They're all the same. Okay. So we got a cube missing a side, and then we have a pyramid. Okay. Now, when we go to start considering the pyramid, one of the things we need to figure out, do we need to add in some more surface area because the pyramid is missing, or are we subtracting surface area because the pyramid is missing, or what? Yeah, and that's the problem. Here's where we get a little crossways with it. Okay, we are actually adding surface area because there's a pyramid missing. And that kind of goes the opposite of the way your common sense is going to tell you. Okay, but we're adding in surface area because if the side of the cube had actually been there, we'd have been able to come straight across the top of that thing and we would have been done. But since the top side of that cube wasn't there and the pyramid goes downward, now we've got extra sides to have to consider where there shouldn't have been any extra sides. So that actually causes us to have additional surface area. And we're going to have an additional pyramid. Oops. I can't spell it. And as some of you are already saying, do we want the entire pyramid or no? Okay, we don't want the entire pyramid. Okay, what's the pyramid missing? It's missing a base. How many bases is it supposed to have? One. So do we want a formula that even talks about any bases? No, we don't need a formula that talks about its bases, so we will pick on the formula that talks about the lateral. Okay, so go to our formula charts and figure out what's what. Okay, how do you find the surface area of a cube? 6s squared, exactly, straight off the formula chart. Okay, but that would be for all of the sides. Do we have all the sides? No, we don't. How many do we have? There are 5. So what we're going to do is take the 6 off of that formula and replace it with a 5. So we only want 5 sides of the cube. To that, we need to add the lateral surface area of the pyramid. Okay, got a formula for that one? Not sure what problem Isaac's looking at over there, but here in geometry class, we've got a pyramid 1/2 PL. Okay. All right, now that's a simple enough looking formula, certainly the easiest one, the easiest looking one that we've seen so far. Let's see what we've got. We've got 5, which needs to be multiplied by side squared. Do we know the measurement for side? Okay, side of the cube's 23 millimeters, so that's easy enough. Okay, plus 1/2 times P, capital P, that's the perimeter of the base of your pyramid. Okay, how do you, yeah, we got 23, 4 times around, okay, and that ends up being 92, thank you. Okay, it's 4 times 23 if you want to jot yourself a note down if you have trouble figuring out where numbers came from later on. It's 4 times 23, that's 92. And then the lateral height. Okay, so here's where we're at least partially stuck. Lateral height would be from the vertex straight down one of the edges and make contact there. Okay, so filling in the rest of that information, we kind of need to know what's going on inside of that triangle. We got lateral height. What other measurements of this triangle do we know? Okay, 23 would be the overall vertical measurement of that triangle. What else? Yeah, half of 23 coming across the apothem. Okay, the apothem there would be half of 23, 11.5. Now, it's just a triangle. We're going to have some decimal points in it, but you know what? Life goes on. We got 11.5 squared plus 23 squared equals the lateral height squared. Okay, no idea what these values are. Well, I know what 23 squared is, but I do not know 11.5 squared. But this is easily found out. 11.5 squared plus 23.5 squared is 661.25. Okay. So if we take the square root of both sides, we'll find out what our lateral height is. So I'm going to go square root of the answer. Okay. And once again, we've got a big pile of decimal points. Okay. So yeah, we might be able to get all this information in there using the answer function. But again, you can just store the value. Go store, and since we're finished with the old problem, I'll just store a new value for A. Okay, calculator's got it saved for me. That's our lateral height. Okay, so from there, okay, we ought to be able to figure this out. We got 5 times 23 squared. That's 2645. 1/2 times 92 times A. 1182.88. Plus 2645. 3827.88 what? Millimeters it was. Second dimension. Okay. So again, you cannot eyeball the questions and decide which ones are going to be difficult or hard. So don't just automatically freak out every time you see a hemisphere or a triangular prism, because it's very possible everything might be provided for you and you don't really have any calculations to do. It just depends on what the problem has compared to what the problem needs. But that's the way surface area works. Okay. So we've got an assignment to go with this. Let's get to that.